Let's do the last part of the unlearning module, which is graph unlearning. If you can think about what could be graph unlearning, until now we talked about unlearning, machine unlearning. We're generally talking about text, generally talking about images also, right? But what is graph unlearning? Here are some applications of graph that you may have seen. Some of them you may have even worked on or probably even are part of. This definitely most of you must be part of. Healthcare networks, you go to different hospitals, hospitals are connected, doctors are connected. Biological networks also, they are all meaning neurons, connections, are meaning the way I'm speaking now is because of lots of things are going on in a graph form also, right? My body is sending different signals to show my hand like this and to process something, to look here, all of that. Adversarial settings, of course, treat this as, let's take a network of people connected, and then there are bad people who are trying to do some things in the network. Financial networks, different banks, different users in the bank, people who are deciding on what the stock value should be and all of that. Transportation networks, of course, you must have seen the Google Maps and the train maps, subway maps, everything. Collaborative environment, you must be doing projects which are between groups, between institutes, between probably countries also. This is network of devices where multiple devices are connected and they're all sending signals for deciding on something and collecting data about, let's take energy, power, water, all of that. Let's take light posts in your society, in your college, maybe sending out information about when all it was on, when all it was off, and when the bulb is broken, can it send out some messages. Okay. You must have heard this word called GCN, Graph Convolutional Network, but I thought I will just do a refresher and then I'll move on to the idea for why we are looking at GCN and what is the connection to graph unlearning. Graph Convolutional Network, GCN, was introduced by Thomas and Max. The key idea here is that a GCN layer defines a first order approximation of a localized spectral filter on graphs. Keep that in mind. GCNs can be understood as a generalization of a convolutional network to graph structure data. Right? It's an idea where convolutional neural network, which is something you must have seen. Actually, if you would have seen the initial weeks supplement content, you must have come across the CNN word, and then you must have also seen many methods, how to analyze them and all that. Understood as a generalization of a GCN is a generalization of a convolutional neural network, particularly for the graph data, which is what this graph is, this slide is. The formal expression of a GCN layer reads as this. Let's look at what are they, right? H is a matrix of a node representation. Node is this. For example, this is a node. This could be a node. This could be a node. Right. User could be a node. Node representation HU. X is the matrix of node features, XU. And sigma is an activation function like a ReLU. It's a graph of an adjacency matrix with the addition of self loops. Right? Network, the thing that could happen is that there could be a self loop, right? For example, you could like your own post on Twitter. Right? So that's, if I were to put that in a graph, that could be the self loop. And D is the graph degree matrix with the addition of self loops. and theta is a matrix for trainable parameters. Okay. So if you keep all of this in mind, which is part of a graph itself, node representations, node features, activation functions, adjacency metrics, degree metrics, and some parameter for which can be trained. Right? So that's what a GCN layer is. Why is this important for us? If you think about it, and then the reason why I connected this is you really want to understand this idea of GCN, because in the graph unlearning methods, many times you're going to use this either the function or the modified version of these functions. One idea, one intuition that you need to also understand for graph unlearning is that in the graph, if you see, a node is generally having features and information that could come from the neighbors of that node also. Right? So let's take your Twitter network, you're influenced by the neighbors that you have in your network. Right? You could, I mean, let's take in your society, there are certain things that you may do which is very similar to what your neighbors are doing. That's what message parsing idea here is, but the intuition here is to get a node feature which is coming from the neighbors. Okay, let's go through some idea in more detail of this. Message passing layers are permutation equivalent layers mapping a graph into an updated representation of the same graph. Formally, they can be expressed as a message passing neural network. That's what we are interested in. Message parsing neural network. GVE, that's the graph. If you have taken any graph theory class, this must be very simple for you. Be a graph. V is the node set. Again, V is the node set in the graph. These are nodes. And E is the edge set. So this is edge. This is V. And let NU be the neighbor of some node U contained in V, which is all the neighbors. For example, this user has the neighbor as, let's take A, B, C, D. So A has neighbors as B, C, D. Let XU be the features of the node of U. So then features also, right? You want to know that, oh, height, weight, color, college, courses that they have taken, all of that. And UV be the features of the edges UV. So the message parsing neural network, which is what we are talking about, can be expressed as this, which is using all these things that we saw, where phi are differentiable functions particularly, and this is a permutation invariant aggregation operator that can accept an arbitrary number of inputs, sum, mean, max. So it's basically a function. Let's take this is any of these functions called sum, mean, max. This is referred as update and message functions respectively. Update and measure functions respectively. In an MPNN computational block, graph nodes update their representation by aggregating the messages received. So essentially, I wanted to get across this intuition, so I kind of brought all of this here. In graphs, graph nodes updates their representations by aggregating the messages received from their neighbor. This is getting aggregated by messages received from others. Okay. And then the idea is that node representations can be employed for any downstream tasks such as node graph classification or an edge prediction. Classification is that, oh, look, this node is there. For example, this task that we talked about, right? Is this a good node or a bad node. That's a node classification problem. Edge prediction problem. Oh, look, this user A is connected to E. A is connected to E. B is not connected to A. What is the chance that they will get connected? Very good link prediction problem also it's called, but very good context for finding out recommendations in a Twitter network or any social network for that matter. So within the graph unlearning, there are 3 ways to do unlearning. First is node feature, node unlearning, and edge unlearning. Let's see what they are. If you think about it, node feature unlearning is I have a graph, I have a feature for the nodes. I just want to unlearn that. Feature being, let's take, I want to unlearn that PKA works at IIIT Hyderabad. That's the feature. Node unlearning, I want to remove PK from the graph. Edge unlearning, I'm PK and let's take somebody X, prof is connected, and now I want to remove this edge between PK and X. That's the edge unlearning. Those are the 3 things that you can do, right? One is node feature unlearning, the other one is node itself, and the other one is edge unlearning. So here is a figure that explains it. So in this case, this is edge unlearning. In this case, it is feature unlearning. In this case, it is node unlearning. Right? Graph ML methods. These are here. GNN, GC, and all that we spoke. And then these are, so we'll just look at what are the different types of methods you can do now in next slide. But graph unlearning methods, there are different methods to do the unlearning, and then you get the output. Graph, different ways of learning. You get M, and then you get M dash, which is the unlearned model. The graph unlearning framework is illustrated. It depicts the 3 types of removal requests, namely node removal, edge removal, and node feature removal. Each of these requests represent different scenarios where specific elements are to be removed from the trained model. Again, feel free to take a look at this paper. Right. Okay, so let's move on. So again, this is available in this paper in detail, but I wanted to emphasize on some models, some methods for graph unlearning, which is graph eraser, guide, projector, and graph editor, and GNN delete and MEGU. MEGU stands for Mutual Evolution Graph Unlearning, but here are the 3 methods that we just now saw for unlearning. These are 3 things that we can do unlearning on: node, edge, and feature. TIG says that a graph eraser does node unlearning, graph eraser does not do feature unlearning, which is it can't remove PK as a professor at IIIT Hyderabad. Whereas it can remove PK, and it can remove PK connection with a professor X. This column gives you the intuition on what the idea is. They use sharding. Sharding is hard. This column gives you the disadvantages of the method. Guide is a method, and this can do node. This cannot do edge, and this cannot do feature. It optimizes on the partitioning and graph aggregation methods. Again, this also uses sharding method, so which is hard. Projector is a method which does only feature unlearning. Project the weight parameters where the features to be forgotten are irrelevant. Right? Wherever the features are to be relevant, it projects that and works only on a linear GNN. Graph editor is again does all the 3. leverage on a closed form solution to first efficiently remove the effect and deleted nodes, and then update the effect of the neighboring nodes, right? So first it does the node and then it does the neighboring node. Again, my intent here is because these can be slightly intense, but the idea is that, look, there are many methods. The methods do a lot of these things, and you have to understand the intuition for how these models work and some disadvantages of these models. GN and delete and MEGU does all the three, introduces shard weights matrices across nodes and use layer-wise deletion operator to update the model instead of, this does at a layer, at every layer. Cannot handle unlearning requests for continued learning, which we also saw before, right? Continued learning, you want to keep updating the model very regularly. It is very hard. You can take this GN and delete, can take requests for unlearning, does it all of them, and then produce the model. The latest one that we have come across is MEGU, so therefore we have not seen any disadvantages of it, at least for now. Adaptive high-level influence neighborhood selection for custom loss function. It decides on what neighbors to use for deciding on the features, that messages that it can take. Put both the URLs here for where the different methods were taken from. Yeah, that's a big list. It's the same link from the last slide, but full list of all the methods that we spoke and all the different method summaries that are there in the column in the earlier slide also. Okay, some problems with generally about graph unlearning. Most methods focus on forget set, which may impact the performance of the retained set. Often models also tend to over forget information, right? So that's the thing that I've been emphasizing from earlier. You want to make sure that the forgetting that we do, unlearning that we do on the model does not over forget. Particularly graph methods do. That's the point here. There's less focus on continued learning. That is, it is possible to continue to train the model after forgetting some information in deployment. That's, can the particular model be used in real world scenarios without excess override? So I think this continued learning, I just now mentioned this continued learning here, right? So that is hard in graph unlearning. Are the methods actually forgetting information, and is the performance being affected too negatively that is unusable in the reality? How to test these metrics properly? I think these are good questions to ask, good research questions that if you're interested, you should take up as ideas. Something I also mentioned in the first week of content, I think. But these are areas that are becoming very, very active area of research now. So if any of you are interested, please pick a idea, think of it, come up with a method, come up with some things that you want to try, if not method, right? Some things you want to try, we can talk about it and you can take it forward and see how you can try it out as part of this course. Okay, so that's what is there. So one of the things that I would leave you with for this module is an activity. So the deadline for this activity would be Saturday. And when you submit this activity in the mailing list, please add activity #unlearning as in the subject line. This will be a standard thing that I would request you to do. All activity slides, when you submit, please put the subject line as the activity slide text. There are 8 methods to evaluate robust unlearning in LLMs here. Take a look at them. So this one you should be able to play around yourself to reproduce these attacks on the Hugging Face checking point of the Harry Potter Unlearning. Remember I showed you about Harry Potter Unlearning table. You should be able to go do it yourself and try out something on the Hugging Face interface and post what did you try, what did you get, and was there anything interesting. If you can share on the mailing list, that will be super cool. Thank you for joining this module. Hope to see you in the next module.